Hey friends and fans of Bob's Retro Electronics Workshop. Last time of course we did a couple of AC power supplies. This you should all recognize as an original Commodore 64 power supply, the Death Brick. I see guys retrofitting these with new transformers and such, so I'm going to give it a try. I think maybe, I don't know if I can. I don't think that's going to work, but I see most of them just pry right here, carefully. You know what? I did this before, where I rapped on it. To shock and crack the glue. And I'll bet you it helps. Alright, let's see what we did. Couldn't have done any harm, could we? Oh yeah. Oh, one corner's up already, good. We want to be... I guess I'm being pretty hasty, but I shouldn't be. I want this to end up... Okay, I'm pushing the screwdriver with my thumb and twisting upward at the same time. Okay, that's cracked, so I'm going to go around the other way. I've got it on top of the epoxy on the inside, which I don't care about because we're taking that out. Okay, I'm going to try the old whack the X-Acto knife. As broke the blade off, but that might actually help because I can dig the corner down in. Maybe I can... Oh yeah. That cut right along there, just nice. You know what, there's webs of this down into the... Yeah. There we go. We're getting there. Jam this in between the plastic here. I haven't done too much damage, I don't think. What the heck is holding that? It's up a 1/4 of an inch. There we go. Oh, these little pins. Alright, well, there we go. Now we need to try to save as many of these longest leads as we can. So we're going to try to dig this stuff out of the epoxy, just like that. That's the AC line and the ground, which the ground's nice and long. And there's the wires, outputs to all the connectors, and that looks like we got, that goes right to the transformer here, so that's good. Of course this isn't plugged in, duh. we're going to have all the lead length we need. Now I think one of these slots is bigger and one is smaller. Yes, see, it's a little bit bigger I think for the AC line. Now how do we get this thing out of here? I'll tell you what we're going to do. I'm going to cut off these plastic nibs. We're going to crack it free. I wonder if I got some oil of some sort. I'm going to just wrap on this to knock it free. And I'm doing that gently. You don't want to break the plastic box. I heard it snap free. Okay, so these guys snapped it on the floor. So I'm going to get a piece of wood. Oh, I've got a piece of wood right here. It's actually a piece of firewood. And I'm going to try to knock it loose. I heard it crack already. It's almost out. Look at that. It's loose. Now I just need to, what I saw a guy do, he put blocks on both sides of it. So it gave it room to come out. Okay, but it's loose. It's dropped about ½ inch. I need a couple blocks of 2x4 or something. So, I'm going to zoom in a little bit. I'm not sure exactly how well this is going to work because the edges of these 2x4s are pretty rounded, and so is the power supply box. But I'm going to try. Now see, he had his all screwed together. This isn't going to work very well, I don't think. Because I'm not going to be able to lift this up. Oh, come on a little bit. How about if I put it, here's the square edges, okay. Oh yeah, she's coming, she's coming. This is not the way to do it. Make yourself a box and screw it together. That's the way I've seen it done by the other guys. Here she comes. All right. So I see what looks like a fuse embedded in here. I'm going to try and see if I can recycle the original transformer. Let me get this up on the bench. Alright, well, we know it's going to break apart right there. I'm going to make a mess. There's the AC input. Now that's a very, very fine wire, but that can be salvaged. I broke off the center tap. We'll have to see Well, there's the heat sink through the 7805. I may or may not use this. I'm just curious to see what's in here. Anyway, I'm not going to be able to get into this. There's the filter cap. The rectifier takes your AC waveform and turns it into a pulsed 120 hertz pulses, and then those pulses feed into these capacitors, and the capacitors work like a reservoir, like an air pressure tank. They build up the electrical charge and feed it back out into the circuit and take what they call the ripple out. And so what you need to do is have the voltage on that capacitor high enough that when you're drawing current out of it, it doesn't dip low enough to get below the voltage that you're regulating at. And so that's, you need a few mathematical calculations when you do your math for design, which is what electrical engineering people do. Alright, we're going to clean this mess up and we'll fart around with that. Alrighty. Let's see what we got here. I want to tie a knot. See, I could take this carpet off and shake it. I'm going to tie a knot near the end of this cable so I never accidentally plug it in thinking it's something else until I'm ready to use it. So we're gonna wad this up a little bit here. Same thing goes for the power supply leads, the main leads. It's a little crusty looking, but I do have deoxit. I'd like to clean it up a little more, but I don't know if I can. You guys have seen other guys do this before too. I learned how to do some of this stuff from them. But I want to see what we got. So why did these things, they turn like a can of worms in mating season or something here. Yeah, let's do this. This has little fine clips on it. Okay, let's just put this on ohms for right now. Can you guys see the ohms? Oh no, that glare is so nice. Can I turn the backlight on? Somewhere here there's a light. Oops. We're just gonna probe this guy and see if we can figure out what coils are what. Now these do usually have enamel coating on them, which means they are difficult to. I've screwed up my utility knife here. We're gonna scratch all of these. So I got two. We got to find out what leads are what. That's what we got to do. See if this reads 0. Okay, pretty close. I'm going to dive in here with my headset on. See if I can find anything. Let me make sure I scratch a good spot here. See, there's clear enamel on these wires to make them insulated, of course. Okay, so we'll try to clip that guy in there. Oh, I got something there. Okay, so there's 0.6 ohms. That's a good strong coil, which you need a low impedance coil to get your high current out of. Okay, so let's see if this connects to anything else. Doesn't seem to attach to that one. I know I broke my razor blade off, didn't I? And this should be common. I got a feeling that these two are in parallel, kind of like. So that shouldn't read anything. That shouldn't read anything, and that one does. Okay, so now those two are together. I'm betting that these two will be together. And if they're in phase, you can wrap them together. Oh, there's a third one. Egad. I really botched this up. There may be a center tap in here. Okay, so we know that one goes to there. Let's try this guy too. Okay, but that one does. There's another 0.7, so there's two windings there. These guys seem to go together. And what we can do is basically, all we got to do is hook up the input and start measuring outputs. I just got to get these scratched clean. Because there shouldn't be anything wrong with this transformer, to tell you the truth. It's a little large, that's all. See, on this side it's got that 1 meg resistor, and I think that's just to limit current. I know for a fact that this is going to read maybe 30 or 40 ohms, or maybe even more when I hook up to the input. My furnace is going to start here. Seems like I put a new blade on this. Alright. Let's see if there's any way I can get any kind of reading out of this. Try my other probes, because it's hard for me to get a clean spot on these. So I'll try just scratching around with my other probes here. We've got to have an input. It was working when I started, and I just don't believe that what I did would have See? I got like 12 ohms, what I could see. Yeah, because the input windings are very fine and there's a lot of them. So what I need is I have a variac around here that I can vary the input voltage. So I'm going to try to solder onto these leads some wires. I'm just eliminating this 1 meg ohm here. I don't know exactly why that's there, but I don't need it. I'm going to see if I can solder some fine leads onto this to start with. There's some more chunks of epoxy. Alright, let me get that soldered on. So, new battery. I'm going to try tacking these down to these leads. I think I'm going to put some tape around here first, like so, to take the strain off these, because I don't want these yanking on these little wires too much. So don't mess around with line voltage if you're not totally competent. I was an electrical contractor for nearly 10 years, and I've done electrical work for ages ever since. So here we are. We are on an insulated table, which is insulated by the carpet, of course. I'm not going to touch the transformer body right now. I'm going to hook up set my meter. See what we can see here. Okay, now I got 117 volts. I'm going to take the trouble to unplug this, and I'm going to tin all these leads. Okay, so you don't have to watch me do that. I'm just going to scrape and scrape and scrape and put solder on there so they're easy to make contact. Alright, got those tinned again. Now we can hook up that other light probe that I have that will grip. And we're going to look at volts AC. Alright, so what do we need? We need to hook this guy up. We need to plug in. I always throw the lead off the bench so it does not get plugged in unless I want it to be. Alright. Now let's see what we got. Originally we were getting 10.5 on this one. Yeah, okay. I think that's one coil. Let's see what we get to this one. See, that's the center tap. I'm betting if we go across these two, we get the 12. That is a plus and minus. I'm thinking the center tap of that touches together. These two right here. So I'm going to try twisting them together. Oop. I'm going to unsolder. Or unsolder. I'm just going to unplug. I'm going to solder those two together. I think they were twisted together because they were right side by side. Alright, now let's plug it back in. Yeah, I don't see any reason to change this cable. So now, if I hook the center tap on here, I should get like 6 and 6. Okay, now I got 10.5. 10.5. And 10.5. So, and if what happens if we go across? (21 volts AC). So you could do several different things with this. I'm still thinking that 10.5, you could do a half wave rectified off on each side, if you understand that. Instead of having a bridge rectifier, all you do is you reference your neutral, your ground reference of your circuit to that center tap. You have one diode coming off with the positive feeding in. So two diodes come together to a capacitor. So every time this changes polarity, you get one positive pulse into the capacitor. That's called a center tap half wave, and I believe. And then that other 10 volts. So I've got all kinds of power here I could use. Yeah. I don't know. I got to look at the schematic and see if I can figure out what would be the best way to use this. But there's no reason we really couldn't use it. We'd have to figure out some way to attach it down into the system. Okay, guys, I want to let you know that I nailed it. Didn't I tell you that that one winding we found, well, that seemed separate, was for the 9 volts AC out, and that the center tapped one, now you can see what I told you. Those two leads I twisted together, they're two sides of two 10 amp or 10 volt coils. They come together each side through a diode into a filter capacitor, through a regulator, and out. So it's exactly what was in there, and it was just exactly how I had it nailed. So we're going to use the appropriate part of the winding here, if I ever get to doing this. And pretty easy, huh? Pretty easy. That way it saves a rectifier by just using the right kind of transformer. Bridge rectifier, save some room. You just got to filter caps in here. And I'm not sure what this 3052P is. It looks like a PNP transistor with a 300 ohm resistor. I don't know how that actually regulates that well. I don't see any regulation on it. It doesn't have a Zener diode or something to control the base. But that's how it's set up. Alright, guys. So that's it for now. We have seen what's inside that power supply. We've seen the transformer. I couldn't really tell you much about what was inside the voltage regulator because it was too well potted and everything got broken. Alright, guys. I had a great idea. I found out that this is a 5 amp or a 5 volt 2 amp voltage regulator IC is all this 3052 is. They drew it as, it looks like a PNP transistor, but it really isn't. Maybe it has a PNP pass transistor in it. All we need to do to produce protection for this circuit is we need to add a crowbar. And what that would be is we need to add a fuse here. Okay. We need to add a Zener diode at, I think, 5.6 volts is about as close as we can find. It needs a resistor in the bottom, 300 ohms or so. And then we need to add a thyristor, which is basically a big transistor that has a breakover voltage that latches. So we put this SCR in here. I'm not sure exactly what the symbol is. And what happens is, this is a 5.6 volt Zener diode. As long as this voltage on the output stays under 5.6, no current will pass through this Zener, and therefore nothing happens to the thyristor, is what it's called. But if it should reach 5.6 volts, this thyristor turns on and latches. It stays on as long as current flows. Well, what does that do? We don't connect it to the 5 volts here, do we? No, we loop over and we connect it back to the input. That protects our regulator and the whole rest of the circuit, and what happens is that basically just shorts this to the ground, the neutral, and if this is like a 2 amp fuse, it'll blow that fuse. Pop it real quick. Our circuit's been protected. So let's rebuild this. I may have to order parts. And I'll redraw the schematic here a little bit clearer. Here. We'll just continue this line out. Okay, we'll extend the wires. Okay, that's still got to connect back there, but what we're going to do is we're going to put our Zener diode, which the symbol looks a lot like that, a resistor, to ground. As long as this is 5.6 volts, as long as this stays below 5.6 volts, that's what a Zener diode does, is when you start putting voltage through it backwards, it will break down at a predictable voltage. So if I could find 5.3, that might be even better. We'll have to look around. And when it does, you feed this current over into your thyristor, which basically I think is drawn like a big diode. But we're going to jump over this and feed this back to the fuse. And that will protect everything. The only thing that'll happen if this voltage ever goes higher than 5.6 volts, it'll blow the fuse. Now again, if we can get this to be a 5.3, even better. And I think they're available. We just got to make sure we control our regulator so that it doesn't ever get over 5.3 or we blow fuses all the time. Alright, but the circuit stays the same. So I'm going to look into, yes, this is linear, which means we will dissipate heat. A switching power supply runs pretty cool. What I want to do is I'm just going to reuse the good old Commodore heatsink that we were given in the power supply. So we've got room in here where we can put our little circuit board with our components on it. We'll just make up a little circuit board. We'll attach our thyristor to this. I might even have a 7805 around here, which I think is plenty of current. And I might even have a 5.3 Zener. Okay, that's the plan. Alright, well I guess it pays to be a hoarder. I'm going to show you. I back up a little bit here. I actually found a LM323 regulator, which is a 5 volt 3 amp linear regulator. It does have short circuit overload protection and all kinds of stuff on the inside, but we're still going to crowbar it. And if I turn this on, you'll see my meter goes up to 9.4. And I had a resistor here that was good for about 1.5 amps. It was 3 ohms, and it still held at 4.92. So that's a good regulator for us. That'll supply more than an amp, and I think that's all the Commodore needs. I could not find, I've been digging for an hour, I couldn't find any Zener diodes or SCRs that would work. So I'm going to have to order something or check with a friend. And if I can find a 5.3, see, that'll be perfect for that 4.92. It'll never go over the voltage that I'm looking for. There's a 337, but that's an adjustable negative regulator. So anyway, we've got to start. I have the heatsink. This is just for giggles. We want to make it work because we're engineering this, aren't we? A fixed regulator is a simple way to do it. It's got all the Zener diode stuff inside. If you look at it, it's just got a pass transistor and a Zener diode in there, basically. And where did I find that 2.7? So there's that 2.7 right there. Okay, 2.75 volts should be about 2 amps because it's half the voltage. And you can see it dropped 490. And I don't want to heat that up too much because there's no heat sink on it. That's a lot of juice on that one little chip. Because what happens is when you have 15 volts in here, we're dropping 10 volts across that at 2 amps. That's 20 watts of power. That's a lot of power through that little IC. So we may have to cut some slots in our Commodore power supply. I may do that. In between here, I might take a slitting tool and cut some slots near the regulator so the heat can flow through. It'll be cool when we get done anyway. It's going to be a project. So we'll get to that.